This problem is about dividing two integers, and we are not allowed to use some specific operations. So we're not allowed to use multiplication, division, and the mod operators. And we must truncate the remaining any remaining values. So there will be no remainders, no multiplication, division, or mod operators. And so when we think about dividing any two values, we can think of it in terms of the divisor, which is A, and we're trying to fit as many A's, so divisors, into B, which is the dividend. So what that effectively is doing is simply a bunch of subtractive steps on the dividend. And those number of steps, n, is the actual quotient. So um, think division in terms of uh, recursive n steps of subtraction of A from B. And that kind of allows us to keep dividing without using the multiplication or division operators. And so initially we can think of keeping track of the quotient, and the quotient is simply just the n times that we are recursively subtracting some value. And so we were kind of wanting to initialize that to 0, and then we will work on building that. Another thing is we want to initially just try to deal with completely divisible numbers first, and then we will try to handle the remainders if there are. So we can do while the dividend is going to be greater than 0, we want to kind of keep subtracting. So you want to do dividend minus equals the divisor, and then we want to update the quotient, but we only want to update the quotient if the dividend is still greater than or equal to 0. Otherwise, we are already negative, and so we don't want to add a full quotient value. So if dividend is greater than or equal to 0, then we can do quotient plus equals 1. And then we want to return the quotient. Some things that immediately we must deal with. So we need to think about negative values. And we know that either A or B can be negative. And if it is negative, then it doesn't really matter until the final answer. So if the answer is negative, then we simply flip the quotient value to negative. And so it won't really affect our division step, but we do need to know whether or not either one value is negative. And there are only two cases where something can be negative. It's either A is positive and B is negative, or A is negative and B is positive. So we want to kind of keep track of those values, and we can keep a Boolean that keeps track of that. So it's negative Boolean equals false, and then and then we want to keep track of what the absolute values are. So the way we know if either one is negative or positive is seeing whether or not the absolute value of the dividend or divisor is not equal to the dividend or divisor itself. So we kind of want to keep track of the absolute value of both of these inputs. So absolute value of divisor is just going to be ABS divisor, and then the same thing for the dividend. And if we can handle both cases, so if absolute divisor is, or we can do the other way, if divisor is not equal to absolute, divisor and the dividend is the same as the absolute dividend, or the second case will be divisor is equal to the absolute divisor. So that means both are positive. And the dividend is not equal to the absolute dividend. So these are both cases where either one is, well, both have different signs. And so if either of those cases is true, then we know that we must flip the switch to as negative to true. And when we're doing the actual division step, so we're doing recursive subtraction here. And as we mentioned that the subtraction does not, well, the division does not matter whether or not like the dividend or the divisor is like positive or negative. So the signs don't matter here. That's why it's important that in order for the actual subtractive step to work, we are only dealing with the absolute values. So we can think of like a simple example that we want to kind of prove. Let's say we are trying to do a equals 5, b equals 25, and either a or b could be negative. So if we like did not work on the absolute values, then it would kind of be we could lead to like increasing the dividend value or like the divisor, which is not what we want. So we're going to try to keep on like decrementing the absolute dividend, and we're going to subtract the absolute divisor. And then we can change all of these. If absolute value, then return quotient. And when we're returning forming the answer, so if is negative, we want to return the negative quotient, and otherwise we can just return the regular quotient. So I would kind of like to add some of these test cases here so that we can keep incrementing our solution as we go. So the first thing we want to like test is whether or not our simple cases work. So we can try 25, 5, and then we can try where either one is negative. So one with -5, and then one with a negative dividend. So -25. And if you run this, hopefully our custom test cases should pass, and then we can build this forward. So turns out all of the test cases passed, and the well, all of the cases involve kind of the same kinds of things that we've been working towards. So again, we are able to correctly handle the remainders here because of this critical step that we are only adding to the quotient if there is a positive value. So this handles remainders. So this means that it works for all of the base cases. And the problem here when we try to extrapolate this recursive function to very large numbers is that it will usually time out, or it will take very long because so this division step is linear time, so it is on, and that is because we are always decrementing by 1. And this causes a bottleneck if you have a very large quotient answer. And for example, if you have like a divisor of 1, but a dividend of like 10,000 or 100,000 or something, it will take that many n steps in this loop. And so we want to think of a better way of doing this. And one way is here, instead of, so every time you're doing this, like subtraction currently, we are always subtracting by 1 and adding a quotient of 1. But we can try to be like a bit more greedy here. So in every single time we are trying to subtract, we can always try to subtract more every single step. And we obviously can't use multiplication, but if you think about doubling as a potential strategy, where every single next time we try to subtract, if the previous subtraction was successful, we can try to subtract twice as much. And that is simply just adding the quotient to itself and the divisor to itself. So we are doubling the subtraction we're doing at both steps by twice the amount until we reach a breaking point, and then where we need to reset and start from 1 again. What we want to do here is, inside of this loop, we would rather set some current divisor, and we will set that to the absolute divisor. And we want to set the absolute, current quotient multiplier, and we can set that initially to 1 because that's what we are starting with. But so the quotient multiplier has to scale with our current divisor multiplier, so we can actually just name both of those to that, and then just initialize multipliers, and both of these will effectively double in sync with each other. So that will allow us to kind of reduce the number of recursive steps. So now what we can do is, while the absolute dividend is greater than the absolute divisor, because as long as the dividend is greater than the divisor, we can keep on adding more quotients, otherwise like we cannot add more. So while it is greater, we want to obviously see or try the subtraction. So the remaining post subtraction, and we can set that to the absolute dividend minus current divisor multiplier. And if the remaining post subtraction is greater than or equal to 0, then we can subtract the actual value. So here we want to do absolute dividend minus equals, or we can set that equal to the remaining post subtraction. Before that, we also want to add the quotient. So quotient will be plus equals the current quotient multiplier. And then after this, we want to effectively double the values. So we'll set current divisor multiplier plus equals itself. And the same thing with the quotient. So current quotient multiplier plus equals itself. And we can get rid of this part and the outer loop. And we should put this in the inner while loop. And we can kind of simplify this. So instead of calculating the post subtraction and keep decrementing the values, when we're doubling, we can instead directly find what the greatest amount we can double is. And so we want to find out what the maximum divisor we can get and the corresponding maximum quotient multiplier. And that's going to kind of just make this a bit more cleaner to code. So we can do another like while loop. So while the absolute dividend minus what the current divisor multiplier is greater than or equal to 0, and that should kind of allow us to keep doubling it. So current divisor multiplier plus equals current divisor multiplier. So we are going to be doing this step here. And that means that this will loop until we find the greatest multipliers we can, and then we can directly do these operations here. And so this means it will keep running, and this should be a greater than or equal to. And that will allow us to kind of do the final addition if there is exactly the quotient, the divisor is equal to the dividend. And here it will be, we don't have post subtraction, we're just doing decrementing the current divisor multiplier. This loop should be at the same level as the function, and in this inner while loop, we need to kind of check whether or not the doubled value is going to be greater. So it's not just the current divisor multiplier, but if you want to double it, we need to make sure that the doubled value is still greater. So we're going to just sum it to itself again. Divisor multiplier. And then this should be good. So if you run this, it should still pass all of the test cases. And the final thing we need to think about is the assumption that we're in a 32-bit signed integer range. And so in Python, there is no such like limit to the integer size, but we are kind of constrained in this problem that if smallest amount we can have is -2 raised to 31, and the largest value can be 2 raised to 31 minus 1. But there is a special case where if we have two negative numbers, so if let's say we have -2 raised to 31 is the dividend, and the divisor is -1, then that will cause an overflow because you will need one extra bit to represent the signed values. And since division by 1 retains the full like length, it is going to kind of require 2 raised to 32 number of bits length, but we will not have that, so that will kind of crash this program execution. So after we kind of calculate these values, we can just hard code the edge case. So that would be if the dividend is equal to 2 mod 31, and it's going to be negative 2 mod 31, and divisor is equal to -1, then we want to return -2 raised to 31. I accidentally wrote a negative. It should be 2 raised to 31, as a negative and negative will be a positive number. and we need to return -1. So also when we're checking for a negative, we should ideally check the entire value. And if you run this, this will pass all of the edge cases and be the optimal solution, as we are no longer doing this in linear time, but this is reduced from ON to O log n complexity, and the kind of maximum like iterations for this quotient is just log 2 of n, and the space complexity is just constant, as we're not using any recursive or even linear data structures. Um, so that's all for this problem, and thank you for watching.